In this problem, we need to find the Laplace transform of the voltage output, I naught S. There's no energy stored in this circuit for t less than 0. So we know in here that we are going to be dealing with time. That is super important, especially for Laplace. And because we are dealing with time, and because our switch is closed, we know that we have some current flowing through here, like this. We have some current flowing through here, and current flowing through here. We're going to be analyzing the current flowing through here because this is our I naught. So that's just super important to know. That's what we are doing. So to solve this, because we know we have all of these currents flowing through here, we're going to use Kirchhoff's voltage law. We know that we have some current going in this way, down this way, and this way. So we're going to need to write this. But before we do that, there are some things that we need to change to be in the time. First thing that we need to change is this VDC. And this VDC, because of time, we need to multiply it by U of t. And if you look in the notes linked below the like button, on page 50, we know the Laplace of U of t is 1 over s. So this, we are going to write V d of c for the direct current is multiplied by 1 over s. We're going to do something similar for this L. This is not just an L. It is now a Z S of L. And normally, when we are switching to impedance, it's going to be J omega L. However, for this, it's just going to be S times L. Similar to this, the capacitance is going to be Z S of C, and we are going to have 1 over our S times C. Now, we're going to look at our I naught, make this in the time. It's going to be I naught times S. We're going to have this V naught times S, and we can see that this inductor right here is in parallel with our capacitor, so we're going to have a plus minus V naught because voltages in parallel are the same. We're going to have a V naught S. And now we can actually do Kirchhoff's voltage law. So we are going to have our voltage right here, because it is the middle underneath our node, minus our source voltage. We're going to have the V naught S minus our VDC, and because it's in time domain, we're multiplying it by 1 over S, so it's just going to be over S. And this is all happening over the resistor. Next, we are just going to have the voltage itself, so we're going to have V naught S divided by our S of L, the impedance here. Next, we're going to deal with the V naught over the capacitance. We're going to have V naught S, and this is divided by 1 over S of C. Per Kirchhoff's voltage law, this is all equal to 0. Now we're going to combine like terms and move the VDC onto the right side. So we have our V naught S, and this is factored out. Instead of here, we're going to have 1 over R. We are going to have a plus 1 over S of L plus S of C. And this is all going to be equal to the V d of C divided by our R of S. Now, to simplify this, we're going to multiply both sides by our R of S. So we multiply it there, and we're going to multiply it in here. So if we do this, we're going to get V naught S, and then inside of our parentheses, we are going to have an S plus R over L plus R S squared C, and that is it. So that is how we would do this instead of equal to VDC. We are going to combine this so that everything is together. We're still going to have a fraction, but there is going to be less separation between the values. So we are going to have an S of L plus R plus S squared R C L, and this is all divided by L. So now they are all together, set equal to our V d of C. Now we want to find our naught right here. So we're going to be focusing on that. So what do we have? Because we have two unknown variables. We have this V naught and this VDC. Well, we can find our V naught. We know what V naught is because we have the current flowing through here and we have the resistance or impedance. So we can find it. We're going to set V naught S equal to the impedance, which is the I naught S, and this is being multiplied by the impedance, which is S of L. And so we can rewrite this because we want to find our I naught. I naught S is equal to V naught S, and this is divided by S of L. So that's how you do that. And now we're just going to plug in our v naught s right here. We have our I naught s, and it is equal to, plugging this in, we actually, before we plug this in, we can see that we have this v naught s times this. And that won't work because we can't really plug that in. So we're going to have to rewrite this as v naught s is equal to vdc, and we're just going to multiply both sides by the inverse of this to get our v naught s by itself. So we're going to have vdc times the denominator, which is now the numerator, which is L, and this is over s of L plus r plus s squared r cl. So that's what we're going to be plugging into here. We are going to have vdc times L divided by, we are going to have our s of L, and then sl plus r plus s squared r cl. And now in here, we know that this L and this L can cancel out, and we're done. That's it. We found our I naught. However, we need to simplify this. Looking at our answers, we can see that we have this s squared right here. Well, we do have an s squared, but it's not by itself. What we can do to get it by itself is multiply the numerator and the denominator by RCL, or 1 over RCL. In doing this, we are going to get that our I naught s is equal to a v d of c divided by r c of L. This is all massively divided by s. Now we're going to go inside of our brackets. We're going to start off with our s squared, and then we're going to look at the r. So we're going to have 1 over cl, and then we're going to have a plus s divided by rc. So let's look at our answers. Well, we know we need an RCL up top, so it cannot be this D, this C, or this B. We have this A. That matches the top. Now let's look at the denominator. The denominator matches as well, so that means that A is our answer, and that's how you'd go about solving for this problem with the Laplace transform.